So I'm going to start today's lecture with a really good question that someone asked about the previous lecture. And this video I'm going to consider to be an optional part of lecture 11. So go ahead and skip to the next video if you want to. Otherwise, here it is if you're curious. So the question was, how is knowing that x1 and x2 as functions are linearly independent functions, how is that sufficient for knowing that these vectors are linearly independent? So remember in the previous lecture we talked about needing these vectors, these columns of a certain matrix, to be linearly independent, and I sort of just skipped over to talking about whether these functions are linearly independent, and I failed to mention why that's even related to whether these two vectors are linearly independent. Yeah, so that's the question. Actually, the original question was, how is knowing that these two functions are linearly independent equivalent to knowing that these two vectors are linearly independent? But this direction of the question is the more interesting or more important one for us. So the other direction, going from knowing that the columns are linearly independent to knowing that these are linearly independent, that's pretty easy to establish. And in fact, I don't think that's what we need anyway. So I'm going to focus on the harder and more needed direction of things. If we know these functions are linearly independent, then we will know these column vectors are. So here's the answer. Let's suppose that the functions are linearly independent. So suppose x1 and x2 of t as functions are linearly independent. Then our goal is to justify or explain why these column vectors are linearly independent. So that means we want to establish that if you take any linear combination of these column vectors and get 0, then the coefficients that you used must have been 0. So assume that you have a linear combination and it ended up being 0. So let's assume that this ended up being the 0 vector. Then our goal is to prove that C1 and C2, the coefficients here, must therefore be 0. Okay, well, one way to use what we know about, we know that x1 and x2 are linearly independent. One way to use that fact is to try to show that C1 x1 plus C2 x2 is 0. So if we can explain why this is 0, then we are done. We are done answering the question. So why am I saying that? Because if we can explain that this is 0, then since I have assumed that these two are linearly independent, I will know that C1 and C2 must be 0. And that was the goal, right? Our goal is to go from this assumption and to end up establishing that C1 and C2 are 0. So if we can explain why this is 0, then we are done. So why is this 0? It's really not clear. So let's start by defining, so let's define x of t to be whatever this function is. Then our goal is to prove that x of t is 0. Then the information we know about x of t takes the form of these two equations. C1 x1 of 0 plus C2 x2 of 0 is 0. So that tells me that x of 0, that's C1 x1 of 0 plus C2 x2 of 0, is 0. And we are also told by the two equations here, the second equation says C1 x1 prime of 0 plus C2 x2 prime of 0 is 0. So x prime of 0 is 0. Okay, now is that sufficient to conclude that x itself must be 0? That's the goal, right? Prove that this thing is 0 so that we can get C1 and C2 to be 0. Are these two sufficient to prove that x itself is 0? Definitely not. This does not prove x is 0. For example, if you had x of t equals t squared, then it would definitely be true that x of 0 is 0 and x of prime of 0 is 0. So that can happen, and then x would not be 0. So what do we do? It's actually not necessarily sufficient. This is not true. It's not sufficient just knowing that these two are linearly independent to know that these column vectors are linearly independent. But if we're talking about solutions to a second-order linear differential equation that's homogeneous, then it might be. So suppose that x1 and x2 are linearly independent solutions to Lx equals 0, where L is like a, the second order linear operator, a d squared dt squared plus b ddt plus c, that kind of thing. So that we're looking at a second order homogeneous linear differential equation. So suppose x1 and x2 are not just any old linearly independent functions, but specifically linearly independent solutions to one of these. Then we have a third condition here. In addition to x of 0 equals 0 and x prime of 0 equals 0, we also have let me write it fully like this: ax prime prime plus bx prime plus cx equals 0. So that means x satisfies this initial value problem. So in other words, that is, x solves this combination of x1 and x2 solves the initial value problem, ax prime prime plus bx prime plus cx equals 0, with initial values x of 0 and x prime of 0 both set to 0. But what else solves this initial value problem? Is 0. So does the 0 function. What I mean by that is, look, a times 0 prime prime plus b times 0 prime. So here I'm using I'm using the symbol 0 to refer to the 0 function. Plus c times the 0 function equals 0. That's true. And if I take the 0 function and evaluate at 0, I get 0. And if I take its derivative and evaluate that at 0, I get 0. So yeah, so does 0. Then since solutions to initial value problems are unique, we must have x equals 0. X of t equals 0 for all t, in other words. So that implies that c1 x1 plus c2 x2 is 0, which implies that c1 and c2 are 0 if you knew that x1 and x2 were linearly independent. So it's all coming from linearity on the one hand. Linearity tells us that, when we assume x1 and x2 are linearly independent solutions, or are solutions at all to the differential equation, then it tells us that any linear combination of them, like this x, would also be a solution to the differential equation. And on the other hand, we're also using uniqueness for solutions to initial value problems. So that is getting involved here. So that might make this whole discussion not so satisfying. And if you find it unsatisfying, I don't blame you at all. We're sort of relying on uniqueness of solutions to initial value problems, but that's not something we actually proved. Still, I'd like you to sort of black box that part of things. So in this course, in Math 4B, you can black box existence and uniqueness as sort of a known thing or the given thing that we start with, and wait until more advanced courses if you want to take them or if you're interested in reading later on, when you're ready for those things, to see how you can actually prove those statements about existence and uniqueness. But yeah, if you're convinced that for a second order linear differential equation like this, knowing initial conditions determines unique behavior for x, then this argument should be convincing, hopefully. Yeah, and kudos to the person who asked this. This is a great question. Yeah, so but all you really need to know when you're working with this stuff is that you need the solutions x1 and x2 to be linearly independent in order to have x equals c1x1 plus c2x2, this notation, to then refer to a general solution. That's all you need to know.